In this video, I want to look at variance. And just like with means, when I looked at the population mean and the sample mean, I want to look separately at the population variance and the sample variance. Let's start with the population variance. The population variance is denoted by a sigma squared. And there are two different ways we might want to calculate it. One of them says 1 over n, the population size, of the summation of all the values xi minus mu squared. This formula here tells us exactly what it is that we're doing. We're looking at how far things are from the mean. We're squaring it to kind of get rid of the fact that some of these are going to be negative and some of these are going to be positive. So we're going to square to account for the different signs so that everything will be positive. We're going to add those up. And then we're going to divide by the number of things. So essentially what we're finding is the average distance things are from the mean. The second formula is an easier way to do actual calculations, but doesn't tell you as much about what we're doing. This one looks at finding the mean of the values of xi squared. So we square all of our data values and then find their mean. And then we subtract the normal mean squared. And in this case, we denote standard deviation by sigma, and it's just given by the square root of the variance. Next, let's look at the sample variance. This is denoted by s squared. And when we dealt with the difference between the sample mean and the population mean, they were essentially the same thing. We just used a different letter or symbol to denote them. But there is an actual difference between sample variance and population variance. We do calculate these differently. For sample variance, we are still going to take our data values and subtract our sample mean to figure out the distance from the mean. Square it to account for the fact that if I just added this up, it would always add to 0. We then add it up, and instead of dividing by the number of things we have, we divide by n minus 1. The other formula is we're going to add up all of the values that look at like xi squared. We then subtract out the number of things times the sample square, or times the mean squared, and then we divide by n minus 1. So this one's a little bit more complicated, but it is occasionally used to help our calculations. And in this case, the standard deviation is just denoted by s, which is once again the square root of the variance. So let's look at some examples of this. Let's suppose we have a certain county that has 60,000 US citizens of voting age, and 36,000 of those are in favor of expanding the use of solar energy. We're going to let 0 denote the people who are not in favor, and 1 denote the people who are in favor. We want to find the population mean, variance, and standard deviation for this data. So let's start with the mean. We have a total of 60,000 people. 36,000 are in favor, which is denoted by 1. And that means 24,000 are not in favor, which is denoted by 0. And if I work this out, I get that the population mean is 0.6. Next, let's work on variance. We can do 1 over my population size, 60,000, times, we need to add these values up, 36,000 times 1 squared, because we need to actually square our data values, plus 24,000 0 squared, and then we need to subtract out our mean squared. And if we work this out, we get that our variance is 0.24. Our standard deviation is then the square root of 0.24. Let's suppose we have a sample of size 50. We have 22 people not in favor of expanding the use of solar energy. I want to find the sample mean, variance, and standard deviation of this sample. So let's start with the mean. We know we have 50 people. 22 are not in favor, which means that 28 are in favor. So if I work this out, I get that the mean is 0.56. What about my variance? I'm going to use the second formula since it is usually easier to calculate that way. We have 1 over 50 minus 1, the sample size minus 1. We need to add up 22 times 0 squared plus 28 times 1 squared. And then we need to subtract out the sample size times the mean squared. And if we work this out, we get that our sample variance is roughly 0.2514. So then our standard deviation would be the square root of 0.2514. Finally, I want to use R to obtain 5 samples of size 50 from the population of voters, and then I want to find the sample variance of each of those. So let's move over to R and look at how this is done. Here I have R, and I need to start by setting up my population. I'm going to let my population vector be denoted by X. We had 24,000 people who qualified to be a 0 who did not support, 36,000 who were a 1 who did support. I'm then going to let Y be equal to sample from this population X, and I'm going to want the sample to be of size 50. And I'm actually going to output two numbers, VAR of Y, that will be the variance, and SD of Y, that will be the standard deviation. I can see that my first sample has a variance of about 0.2057, a standard deviation of 0.45355. And I can continue this. My second sample, the variance is 0.222, the standard deviation 0.471. A third sample has variance 0.244, standard deviation 0.494. My fourth run has a variance of 0.254, a standard deviation of 0.504. And finally, my fifth sample will have a variance of 0.248 and standard deviation of 0.498. So these do not match exactly what my population standard deviation and variance are, but we can see that they are very close, which is very good for us.